Hello students, welcome to my channel Engineering Education. Please subscribe my channel. Thank you. In this lecture we are going to solve problem 11.4 from the chapter 11 Rotodynamic Machinery from the book Applied Thermodynamics by Eastop and McConkey. Statement of the problem is: the following particulars apply to a two-row velocity compounded impulse stage of a turbine. Nozzle angle is 17 degree. Blade speed is 125 meter per second. Exit angles of the first row moving blades, the fixed blades, and the second row moving blades 22, 26 and 30 degree respectively. Take the blade velocity coefficient for each row of blades as 0.9 and assume that the absolute velocity of the steam leaving the stage is in the axial direction. Draw the velocity diagram for the stage and obtain the absolute velocity of the steam leaving the stage, and second, to find the diagram efficiency. So before moving to the solution of this problem, first let's discuss the velocity triangles for this specific problem. So this is the velocity triangles for problem 11.4. This velocity triangle OAB, similarly OAC. These velocity triangles, OAB is the inlet triangle for the first row and OAC is the exit velocity triangle for the first row. So when we merge these two triangles, we get this resultant diagram in which the blade speed is common. This is the blade speed CV. Similarly, looking to the notations, we have used the symbols just like previous problems. This is the absolute velocity at inlet for stage 1, first row. This is the relative velocity with respect to the blade at inlet, and this CRE is the relative velocity at exit. CAE is the absolute velocity at exit for stage 1. Similarly, coming down to this second combination of triangles, these are the velocity triangles for the second row moving blades. So in this case, again we have some notations in which two subscript is used. For example, this is the velocity CAI2, which is the absolute velocity at inlet for stage 2, and CRI is the relative velocity at the inlet for stage 2. Similarly, if we discuss these angles for each setup of triangles, so alpha I1 is the absolute velocity angle at inlet for first row. Similarly, alpha I2 is the absolute velocity angle for stage 2 at inlet. Similarly, for fixed blade, we have alpha I2 and alpha E1. So these are different notations used. Here the difference is only we have two-row velocity compounded impulse stage of a turbine, while in previous problems we have only solved one stage problem in which only one combination of triangles were used. Here we have two set of first row and second row. So this is a little bit more advanced than the previous problems. So given data is two-row velocity compounded impulse stage. Alpha I1 is 17 degree. This is alpha I1. The blade velocity or blade speed is 125 meter per second. This is the blade speed. Beta E2, this is the beta E2 angle. This is the angle making the relative velocity at exit for the second row stage, and it is 30 degree. Beta E1, this is the angle, this is the angle which makes CRE1 with CB, and its value is 22 degree. Similarly, alpha I2, this is alpha I2, and it has 26 degree value. Similarly, K is 0.9. So based on this data, we have to find the absolute velocity of steam leaving the stage, which is CAE2, and second we have to find the diagram efficiency. So coming to the solution of this problem, first we are going to find CAE2 while using this setup of triangles. From here we can find the value of CAE2. So first of all, we know that from this velocity triangle, we know that CAE2 is equal to CB tangent of 30 degree. Looking to this triangle, here we have CB as base and CAE2 is the perpendicular. So beta E2 is 30 degree. So tangent 30 degree CAE2 by CB. So rearranging it for CAE2, we get CAE2 is equal to CB tangent 30 degree. As we discussed in previous problems, that there are two techniques to solve these kinds of problems. First is to draw these triangles to the scale, and graphically we get the values from these triangles. Second method is using trigonometric and analytical approach to find missing things or terms. So we are using the analytical method for this problem due for greater accuracy. So CB value is 125 meter per second and tangent 30 degree. So simplifying this, we get the value 72.2 meter per second. So this is the required absolute velocity of steam leaving the stage, and it is 72.2. So this is the part 1 of the problem, and its value is 72.2 meter per second. Similarly, for diagram efficiency, to find the diagram efficiency, for that we need some analysis to find other missing things. For example, finding CRE2. So for CRE2 from the triangle, it is equal to CB by cos of 30 degree, again from the second row triangle. So putting the values, CB is 125 meter per second, cos of 30 degree. So simplifying this, we get the value 144.3 meter per second. Now finding CRI2 from the triangle, we know that they are related. CRE2 and CRI2 are related like this, 0.9. The basic expression is basically, this is the value of K. So CRE2 is equal to K into CRI2. So rearranging it for CRI2, so we get CRE2 is as calculated 144.3 meter per second, while the value of K is 0.9. So simplifying this, we get the value which is 160.4 meter per second. So now to find other missing velocities like CAI2, for that we will use the cosine law. So using cosine law to find CAI2, so we can write from the velocity triangles that CRI2 square, it is equal to CAI2 square plus CB square minus 2 CAI CB cos alpha I2. So again we have CRI2 is 160.4 square. CAI2 is unknown, we will find it. CAI2 square plus CB is 125 meter per second minus 2 CAI into 125 into cos of alpha I2. So alpha I2 in this case is 26 degree as mentioned in the data. So solving it for CAI2, we get the value of CAI2 equal to 263.1 meter per second. So this is the value of CAI2. Now further we are going to find delta CW2. So it is equal to CAI2 cos of alpha I2 from the velocity triangle. So CAI2 is 263.1 meter per second and cos of alpha I2 is 26 degree. So simplifying this, we get the value which is 236.5 meter per second. So this is the value of delta CW2. Further to find CAE1 in the velocity triangle for the first row, CAE1 is equal to CAI2 by K, which is blade velocity coefficient. So CAI2 is 263.1 and the value of K is 0.9. So simplifying it, we get the value 292.3 meter per second. So this is the value of CAE1, which is the absolute velocity at exit for stage 1, first row. Now finding other velocities in triangle 1, first row. So we can write that using cosine law, CAE1 square is equal to CAE1 square is equal to CRE1 square plus CB square minus 2 CRE1 CB cos beta E1. So Here CAE1 is 292.3 meter per second. So taking the square of this, it is equal to CRE1 is unknown, we will find it. So CRE1 square plus CB value is 125, so it is 125 square. Here it is also 125 square minus 2 CRE1, CB is 125 cos beta E1. Beta E1 is 22 degree. So solving it for CRE1, CRE1 is equal to 404.4 meter per second. So this is the value of CRE1. Now to find the value of CRI1 from the velocity triangle, CRI1, it is equal to CRE1 by K. So simplifying it, CRE1 is 404.4 divided by K is 0.9. So the value of CRI1 is 449.3 meter per second. So this is the value of CRI1. Now further, to find CAI1, which is the absolute velocity attained for the stage 1. So for that again we will use the cosine law, in which for the triangle CRI1 square is equal to CAI1 square plus CB square minus 2 CAI into CB cos of alpha I1. So here we have CRI1, which is 449.3 square equal to CAI1. We will find it. So CAI1 is unknown to us, plus CB is 125 meter per second square minus 2 CAI1, CB is 125 cos of alpha I1. Alpha I1 is 17 degree. So rearranging it and solving it for CAI1, the value of CAI1 comes out 567.4 meter per second. Now to find the value of delta CW1, so for that from the velocity triangle for first row we have CAI1 cos alpha I1 minus CB plus CRE1 cos beta E1. So this expression comes out from the velocity triangle for first row. This is CAI1 cos alpha I1 minus CB plus CAE. Here we have second we have CRE1 cos beta E1. So CRE1 cos beta E1 this length from here to here. This is CRE1 cos beta E1. So solving it for delta CW1, we have CAI1 is 567.4, cos of alpha I1 is 17 degree minus 125 plus CRE1 is 404.4 is calculated. CRE1 cos of beta E1 is 22 degree. So simplifying it and solving it for delta CW1, we get the value which is 792.6 meter per second. Now to find the diagram work output, so diagram work output is equal to delta CW1 plus delta CW2 into CB. So putting the values, delta CW1 is 792.6 meter per second plus delta CW2 is 236.5 is calculated. Let me check. Delta CW2 is 236.5, so and CB value is 125 meter per second. So the diagram work output is equal to 128,638 Newton meter per kilogram. Now to find the diagram efficiency is required in this problem. So diagram efficiency, it is nothing but it is the diagram power output, diagram power or diagram work output divided by input, which is the kinetic energy of the steam. So that is CAI1 square by 2. Diagram work output is 128,638. This 2 will go to the numerator of this, so it will be multiplied by 2 divided by CAI1 square. CAI1 is basically 567.4, so 567.4 whole square. So simplifying this, we get the value of diagram efficiency and it comes out 0.8, while in percentage the diagram efficiency is for this specific problem is 80%. So this is the solution of problem 11.4. Thanks for watching. Please like and comment on my videos. Also subscribe my channel to get new videos.